Hey guys, some devices, they're so unusual, they challenge how we think about our own reality. So in this video, I'm gonna count down 15 of the most unusual devices ever built and what makes each one so strange. Starting with number 15, the Cochlear implant. A cochlear implant is one of the most unusual modern medical devices because it doesn't just amplify sound like a traditional hearing aid. Instead, it bypasses the damaged parts of the ear entirely and delivers electrical signals directly to the auditory nerve. This allows some people with severe or profound hearing loss to perceive sound in a fundamentally different way than natural hearing. A cochlear implant consists of two main components. The external portion includes a microphone, a sound processor, and transmitter worn behind the ear or on the head. The internal portion is surgically implanted under the skin and includes a receiver and electrode array that's inserted into the cochlea. When sound is detected, it converts this into digital signals, processed and sent as electrical impulses directly to the auditory nerve. Now, what makes it unusual is how sound is perceived by the user. The signals don't replicate natural hearing. Early recipients often described the sound as mechanical or artificial at first. Over time, though, the brain will adapt to interpret these signals as meaningful sound, and this adaptation process can take months or years and varies significantly between people. Now, this device doesn't restore normal hearing, and outcomes depend on many factors, including the cause of hearing loss, the age at implantation, and how long the person lived without sound. For some users, cochlear implants enable speech recognition and everyday communication, and for others, they primarily provide environmental sound awareness. Few consumer-facing medical devices like this interact so closely with our sensory pathways. The electrodes will stimulate specific nerve fibers, effectively creating an artificial input channel into the brain. This technology has evolved significantly since the first successful implants in the late 20th century. Modern systems are using sophisticated signal processing algorithms to separate speech from background noise. Despite these advances, though, the core principles are unchanged. Sound is converted into electrical signals. There is also a bit of social and cultural complexity that surround these cochlear implants. Some members of the deaf community view the device as controversial, particularly when implanted in children, arguing that deafness is a cultural identity rather than a condition requiring correction. This debate doesn't change how the device functions, obviously, but it shows how unusual it is for a piece of technology to influence identity and language. It doesn't repair the ear, and it doesn't recreate natural sound. Instead, it teaches our brains to understand a synthetic representation of the world through electricity. Number 14. The Squid magnetometer. So the Squid magnetometer, it is an unusual device because it can detect magnetic fields so weak that they're billions of times smaller than the Earth's magnetic field. Now, Squid stands for Superconducting Quantum Interference Device. It's widely regarded as the most sensitive magnetometer ever built. It operates using superconductivity, which is a physical state in which certain materials conduct electricity with zero resistance when cooled to extremely low temperatures. A Squid consists of a closed superconducting loop interrupted by one or more Josephson junctions. These junctions allow quantum mechanical effects to influence electrical current in measurable ways. When a magnetic field passes through the loop, it alters the phase of the superconducting wave function. Now, this change produces a measurable variation in voltage even when the magnetic field is extraordinarily weak. And because of this, squids can detect changes in magnetic flux as small as a few femtoteslas. Yeah, that's pretty small. Now, to function properly, these have to be cooled to cryogenic temperatures, often using liquid helium. Now, that requirement makes them large, complex, and expensive compared to most sensors. And despite that, though, they're used extensively because no other device offers comparable sensitivity. One cool application of Squid magnetometers is in medical imaging. In magnetoencephalography, or MEG, squids are used to measure the tiny magnetic fields generated by electrical activity in the human brain. Now, these fields are way too weak to be detected by conventional instruments, so using these squid arrays, researchers can map brain activity with millisecond-level temporal resolution. Squids are also used in geophysics to locate mineral deposits, detect underground structures, and even study volcanoes. In physics laboratories, they're used to measure subtle quantum effects and test fundamental theories. In industry, they're employed for non-destructive testing, like identifying flaws in metal components without cutting them open. It's unusual because it doesn't measure magnetism in the traditional sense. Instead of detecting the force or field strength directly, it measures changes in quantum phase. This makes it less like a sensor and more like a quantum amplifier that converts the invisible physical effects into readable electrical signals. Despite decades of development, though, Squids remain specialized tools rather than consumer devices. The sensitivity comes at the cost of complexity, size, and environmental shielding. But it does stand out as an unusual device because it transforms abstract quantum behavior into a practical measurement. It operates at the boundary between physics theory and real-world application. Number 13. The Atomic Force Microscope. The atomic force microscope, this is an unusual device. It can image surfaces at the scale of individual atoms without using light, lenses, or electrons. Instead, it creates images by physically tracing a surface with an extremely sharp probe. This microscope works by scanning a nanoscale tip across a surface. This tip is mounted on a flexible cantilever that bends in response to forces between the tip and the atoms on the surface. These forces can be mechanical, electrostatic, or even chemical in nature. As the tip moves across the surface, the laser detects tiny deflections in the cantilever, which are then converted into a detailed image. The AFM doesn't see atoms like we think of. It measures forces and reconstructs surface features based on how the probe interacts with them. This allows it to image non-conductive materials, which many other high-resolution microscopes cannot do. In contact mode, the tip remains in constant contact with the surface. In tapping mode, it oscillates slightly above the surface, touching intermittently, and these different modes allow the researchers to study delicate biological samples as well as hard materials like metals and semiconductors. One of its unusual capabilities is that it can manipulate matter, not just observe it. Researchers have used these tips to move individual atoms, stretch molecules, and even measure the strength of chemical bonds. These actions are performed with forces so small they're measured in piconewtons. This tool plays a central role in research, polymer analysis, and the study of proteins and DNA. And because it works in air, vacuum, or even liquid environments, it's far more versatile than many other nanoscale imaging tools. But despite its power, it does have limitations. Scanning is slow, and imaging large areas at atomic resolution can take hours. The probe tip also wears down over time, which can affect its accuracy. So these constraints mean that these things are precision instruments rather than general-purpose tools. The atomic force microscope, it turns touch into vision at the smallest possible scale. It replaces optics with physical interaction, and it allows humans to explore surfaces atom by atom. Number 12. The Nanopore DNA Sequencer. The Nanopore DNA sequencer is unusual because it reads genetic code by measuring electrical changes as individual DNA molecules pass through a microscope hole. Now, unlike traditional DNA sequencing machines, which rely on optical systems, fluorescent markers, or even chemical amplification, nanopore sequencers analyze DNA directly and continuously. At the core of this device is what's known as a nanopore, a hole so small that only a single strand of DNA can pass through at a time. This pore is embedded in a membrane and immersed in an electrolyte solution. When electrical current is applied across the membrane, ions flow through the pore. As a DNA strand moves through, it partially blocks the flow, causing characteristic disruptions in the current. Each nucleotide base, adenine, thymine, cytosine, and guanine, produces a slightly different electrical signal as it passes through the pore. Software then analyzes the signal changes in real time and it translates them into a DNA sequence. This allows the device to read genetic information without copying or labeling the DNA beforehand. Now, what makes this so unusual is its physical simplicity compared to its analytical power. Some nanopore sequencers are small enough to fit in the palm of a hand and can be powered by a laptop. Despite this, they're capable of sequencing entire genomes, including human DNA, bacterial genomes, and even viral RNA. The device can also read extremely long strands of DNA, sometimes hundreds of thousands of bases in a single pass. This is unusual because many other sequencing methods break DNA into shorter fragments that must be reassembled later. These sequencers are used in labs, hospitals, and even field settings. They've been deployed in remote locations, including during disease outbreaks and where rapid genetic analysis is needed. Because the device produces data in real time, results can be monitored as sequencing progresses rather than waiting for a full run to complete. Of course, there are some limitations. This kind of nanopore sequencing historically had higher error rates than some other methods, although accuracy has improved with advances in pore design and signal processing. But the Nanopore DNA sequencer is unusual because it blends biology into an electrical signal that can be read instantly, and it reduces genetic analysis from a complex lab process to a direct physical measurement, allowing DNA to be decoded as it moves base by base through a single molecule-sized opening. Number 11. The laser interferometer. The laser interferometer, it's used in gravitational wave detection. This is a very unusual modern device because it measures changes in distance smaller than the width of a proton. These instruments are designed to detect gravitational waves, ripples in space-time produced by massive cosmic events like a black hole merger. A laser interferometer consists of two long perpendicular arms, each containing a vacuum tube several kilometers long. A laser beam is then split into two identical beams which travel down the arms, reflect off mirrors, and recombine at a detector. Under normal conditions, the beams cancel each other out in a predictable way. When a gravitational wave passes through Earth, it slightly stretches one arm while compressing the other. This alters the distance the laser beams travel by an incredibly small amount. The resulting change in the interference pattern is measured and analyzed, and it reveals the presence of a gravitational wave. The mirrors, of course, have to be isolated from any vibrations, seismic, thermal noise, and even quantum fluctuations in the laser light itself. The vacuum inside the arms is among the most perfect ever created, and that minimizes interference from air molecules. The mirrors are suspended by complex systems that allow them to move freely in response to space-time distortions while remaining shielded from external disturbances. Even passing trucks, distant earthquakes, or ocean waves can affect the measurements, requiring constant monitoring and correction. Laser interferometers of this type are not single-purpose machines in the conventional sense. They operate continuously, collecting huge amounts of data and filtering out noise to identify signals. The detection of these gravitational waves in 2015 confirmed predictions made a century earlier, and they demonstrated that space-time itself can be measured as a physical quantity. Now, the device does not produce images or any direct observation. Instead, they translate distortions in spacetime into mathematical signals that have to be interpreted using complex models. The result is a new form of observation that doesn't rely on light, radio waves, or even particles. The laser interferometer. It's unusual because it functions as a ruler for the universe, measuring distances so small that they challenge our intuition. It turns abstract physics into measurable reality, allowing us to detect events occurring billions of light years away using instruments anchored firmly here on Earth. Number 10. Lidar mapping systems. Lidar. This stands for light detection and ranging. It's one of the most unusual modern sensing devices because it maps the physical world by timing how long it takes laser pulses to return after striking objects. Instead of capturing images like a camera or maybe detecting radio waves like radar, Lidar builds a three-dimensional model by measuring distance with light. A Lidar system will emit rapid pulses of laser light, often hundreds of thousands per second, towards the ground or maybe the environment. Each pulse reflects off surfaces like buildings, trees, or terrain and returns to a sensor. By calculating the time delay between emission and return, the system determines the distance with very high precision. When repeated across larger areas, these measurements form detailed 3D point clouds. This gives Lidar an unusual ability to see the structure rather than the appearance. The device doesn't record color or texture in the traditional sense. Instead, it captures shape, elevation, and spatial relationships. This allows it to reveal features that might be invisible to conventional imaging systems, especially when vegetation obscures the ground. Airborne Lidar surveys have revealed previously unknown ancient cities, road networks, and even agricultural systems that are hidden beneath dense forests. Because laser pulses can penetrate gaps between leaves, Lidar can map ground surfaces even in heavily vegetated regions. These Lidar systems are also central to modern autonomous vehicles. They're mounted on cars, they scan the surrounding environment in real time, detecting obstacles, road edges, and moving objects. And unlike cameras, Lidar provides precise distance measurements regardless of light conditions, which makes them useful in low light or complex environments. The device is unusual because it turns time into space. Measurements depend on detecting differences measured in billionths of a second. Even small timing errors can translate into large spatial inaccuracies, so Lidar systems rely on extremely precise clocks and calibration. Lidar also generates an enormous amount of data. Processing and interpreting these point clouds requires specialized software and significant computational power. The raw output looks nothing like a photograph and has to be transformed into usable models. But Lidar mapping systems are unusual. They replace vision with geometry, and they create accurate spatial representations of our world using invisible light and timing alone, allowing us to measure and reconstruct environments that can't fully be understood through images. Number 9. The ECMO machine. The ECMO machine is one of the most unusual modern medical devices because it temporarily replaces the function of both the heart and lungs outside the human body. Rather than assisting breathing or circulation, ECMO fully takes over gas exchange and, in some configurations, blood circulation itself. It's only used in severe life-threatening cases when conventional treatments have failed. Now, an ECMO system works by removing blood from the patient through large cannulas inserted into major blood vessels. The blood is pumped through an external circuit to a membrane oxygenator, where carbon dioxide is removed and oxygen is added. This oxygenated blood is then returned to the body, and this entire process happens continuously outside the patient's body, sometimes for days or even weeks. It doesn't cure lung or heart failure. Instead, it buys time by keeping oxygen flowing to vital organs while the underlying condition is treated or allowed to recover. This distinction makes ECMO fundamentally different from ventilators or even cardiac assist devices. Now, there are two main types of ECMO. Veno-venous ECMO supports lung function only, while veno-arterial ECMO supports both the heart and lungs. The configuration depends on the patient's condition, of course. Both require highly specialized equipment and constant monitoring by trained medical teams. The device itself is pretty large, it's complex and resource-intensive. It includes pumps, heat exchangers, oxygenators, pressure sensors, and safety systems that are all designed to prevent air bubbles, clot formation, and temperature instability. Now, ECMO did become more widely known during outbreaks of severe respiratory illness, including influenza and COVID-19, when it was used as a last resort intervention for patients with catastrophic lung failure. But what makes it especially unusual is how it visibly externalizes life. Blood can be seen flowing through a transparent tube outside the body, circulating through a machine that performs tasks normally hidden inside organs. Few medical devices make our human physiology so physically explicit. But despite the dramatic nature, it's not experimental. It's a regulated, standardized medical technology with decades of clinical use. It turns circulation and respiration into a mechanical process, sustaining our life in situations where our bodies cannot do so on its own. Number 8. The Inertial Navigation System. Inertial navigation. It's one of the most unusual modern devices because it determines position, orientation, and movement without relying on external signals of any kind. Unlike GPS, radar, or radio-based navigation, an INS operates entirely on internal measurements. It uses a combination of accelerometers and gyroscopes to track motion in three-dimensional space. By continuously measuring acceleration and rotation, the system can calculate changes in position and orientation over time. Once initialized, it can navigate completely autonomously. The system doesn't look outward. It measures how the device moves relative to its previous state. This means that the missile knows where it is. It knows where it is because it knows where it isn't. This means that INS can function underground, underwater, inside buildings, or in space, anywhere external signals are unavailable or unreliable. These kinds of systems are widely used in aircraft, submarines, spacecraft, missiles, and autonomous vehicles. They're critical in environments where GPS signals will be jammed, blocked, or intentionally denied. Modern airliners, for example, use INS units as a core component of their architecture. And small measurement errors can compound over time, which causes drift. So to address this, INS units are often periodically corrected using external references like GPS or star trackers. However, during periods where no correction is possible, the system continues operating independently. Advances in microelectromechanical systems have allowed gyroscopes and accelerometers to be manufactured at millimeter scales, and some INS units now fit inside your smartphone, while others are hardened for military or even space use. Early INS tech enabled long-range missile guidance, the deep-sea submarine navigation, and crewed spaceflight, so modern versions continue to support spacecraft when communication delays make external guidance impractical. It builds a continuous mathematical representation of motion based entirely on physics and time, without checking against the outside world. Despite its sophistication, it operates silently and invisibly. Users rarely even notice it, even though it plays a critical role in systems where failure is not an option. It allows navigation without landmarks, signals, or communication, and it relies solely on motion itself. Moving on to number 7, the optical atomic clock. The optical atomic clock. This is unusual because it measures time using the natural vibration of atoms with a level of precision that exceeds everyday intuition. These clocks are so accurate that they would lose or gain less than a second over 1 billion years under ideal conditions. Unlike traditional atomic clocks, which use microwave frequencies generated by cesium atoms, optical atomic clocks rely on much higher frequency light waves produced by atoms like strontium or terbium. The higher frequency allows the clock to divide time into much smaller intervals, increasing precision dramatically. The clock works by trapping atoms in a vacuum chamber using laser light. These atoms are then cooled to near absolute zero to minimize any motion. Then another laser is tuned to a specific frequency that causes the atoms to transition between energy states. This happens at extremely stable and a repeatable rate, which is why it's used as the clock's tick. The clock doesn't measure time by counting any mechanical motion or electronic oscillations in the usual sense. Instead, it measures probability of atomic energy transitions governed by quantum mechanics. The time output is a standard based on the fundamental properties of matter itself. These clocks can measure time dilation over vertical distances of less than 1 meter, makes them not only timekeeping devices but instrument used for measuring gravitational potential. This tech is not widely deployed outside research labs due to the complexity of it. The optical atomic clocks require ultra-stable lasers, vibration isolation, vacuum systems, and environmental control, and even small temperature fluctuations or electromagnetic interference can affect performance. Despite all this, though, the clocks are being studied for future applications in navigation, telecommunications, and fundamental physics. They may eventually redefine the international standard for time, replacing current cesium-based definitions. It simply doesn't track time, it tests physical laws every moment that it operates. Any deviation could signal new physics or previously unknown environmental effects. It turns quantum behavior into the most precise measurements humans have ever created. Number 6. The holographic wavefront sensor. A holographic wavefront sensor is an unusual modern optical device because it measures the shape and distortion of light itself rather than capturing images. Instead of recording what light reveals, it analyzes how the light has been altered as it travels through space or materials. It works by detecting variations in the phase of incoming light waves. When light passes through the atmosphere, biological tissue, or optical systems, it becomes distorted. These distortions degrade the image quality and reduce accuracy of the instruments. The holographic version of this device uses specially engineered optical elements that split and redirect incoming light into multiple reference patterns. By comparing how these patterns interfere with one another, the sensor reconstructs the wavefront shape with high precision. Now, what makes this device unusual is that it operates on properties humans never perceive directly. People see brightness and color, but wavefront sensors detect phase differences measured in fractions of wavelengths. The device translates invisible distortions into measurable data. These sensors are used extensively in astronomy. They allow telescopes to compensate for atmospheric turbulence in real time using adaptive optics. Without this correction, ground-based telescopes would be limited by the Earth's atmosphere rather than mirror size. It's also used in ophthalmology. Wavefront sensors can map imperfections in the human eye at a microscopic level, which allows customized laser vision correction and detailed analysis of visual aberrations. This application measures how the eye bends light rather than relying on standard vision charts. This holographic approach does differ from traditional sensing because it encodes information directly into an optical element, and this reduces its complexity and allows faster measurements with fewer moving parts. However, the design and calibration of these elements is highly specialized. These sensors don't care what the light represents, only how it behaves. The device is unusual because it allows humans to observe and correct distortions in reality at the level of light itself, enabling clearer vision, sharper images, and more accurate measurements across science and medicine. Number 5. The functional MRI scanner. A functional MRI scanner is a very unusual modern device. It measures brain activity without directly recording electrical signals or requiring invasive contact with the brain. Instead, it detects subtle changes in blood chemistry that happen as different regions of the brain become active. From these indirect signals, it constructs maps of brain function in real time. An fMRI scanner is based on magnetic resonance imaging, which uses extremely strong magnetic fields and radio waves to image the body. What distinguishes fMRI from standard MRI is that it's sensitive to changes in blood oxygenation. When neurons become active, they consume more oxygen. The blood responds by increasing blood flow to that region, alternating the ratio of oxygenated to deoxygenated hemoglobin. This change affects the magnetic properties of the blood. The fMRI scanner detects this phenomenon. It's known as the BOLD signal, blood oxygen level dependent contrast. By repeatedly scanning the brain while a subject performs tasks or rests, the device can identify which brain regions show increased activity under different conditions. Now, what makes it unusual is that it really doesn't observe the neurons firing. It measures a delayed physiological response that happens seconds after neural activity begins. Despite this limitation, though, the technique has become one of the most important tools in neuroscience because it's non-invasive and can be used repeatedly on healthy people. Inside the scanner, the subjects have to remain extremely still. Even slight movement can distort a result. The scanning process is pretty loud. It produces rhythmic knocking sounds like an MRI machine, as magnetic gradients rapidly switch on and off. One of the most unusual aspects of this fMRI is how widely its results are used, and sometimes misunderstood. fMRI images are often presented as colorful maps showing active areas of the brain. However, these images are statistical constructs. They represent average changes over time and across repeated measurements, not direct snapshots of thought. This device has been used in medical diagnosis, in pre-surgical planning for brain tumors or epilepsy. By identifying areas responsible for language or movement, surgeons can reduce the risk of permanent damage. It's also been used in legal and ethical discussions. Some researchers have explored whether fMRI could detect deception or unconscious bias. These applications remain controversial, and there's no consensus that it can reliably read intentions or truthfulness. Technically, it relies on complex data processing. The raw signals have to be corrected for motion, noise, and physiological artifacts, so statistical models are then applied to determine which changes are meaningful. Small differences can lead to different interpretations, which is why results must be treated cautiously. But despite its limitations, the fMRI is one of the most powerful tools for studying the living brain. It occupies a strange space between biology, physics, and psychology, and it reveals patterns of activity without ever touching the neurons that create them. Number 4. The Active Noise Cancellation System. Active noise cancellation is one of the most unusual modern devices because it reduces sound by generating sound. Instead of blocking noise with insulation or barriers, it creates an opposing acoustic signal that interferes with unwanted noise and cancels it out through destructive interference. At the core of active noise cancellation systems are microphones, processors, and speakers working together in real time. Microphones detect the incoming ambient noise. The system then analyzes the sound waves and produces an inverse waveform, essentially the same sound but phase shifted by 180 degrees. When the original noise and the inverse wave meet, they partially or fully cancel each other out. What makes this unusual is the speed at which this must happen. Sound waves move quickly, and delays of even a few milliseconds can reduce effectiveness. The system has to detect, calculate, and emit the counter signal almost instantaneously. This requires precise timing, fast signal processing, and careful calibration. Active noise cancellation does work best with lower frequencies, steady sounds like engine noise, aircraft cabin hum, or HVAC systems. These sounds are predictable and easier to counteract. Higher frequency or irregular noises are more difficult to cancel and are often handled using traditional passive sound dampening methods alongside these active systems. The most familiar consumer application is in noise-canceling headphones. These devices continuously monitor environmental sound and adapt the cancellation signal as the conditions change. The result is a quieter listening environment, even in noisy surroundings. But what makes this unusual is that it alters the acoustic environment rather than shield the listener from it. The ear still receives sound, but the sound has been reshaped before it arrives. This can create sensations of pressure or altered perception for some users, especially when the system is first activated. These systems are used in industrial settings, vehicle cabins, and building ventilation systems. In cars, microphones placed inside the cabin can detect engine and road noise, while the speakers emit a canceling signal, and this allows manufacturers to reduce noise without adding any weight and improve fuel efficiency. The physics behind it is well understood, but practical implementation is complex. Sound waves reflect, interfere, and change depending on the space and movement, and designing systems that work reliably across these conditions requires extensive modeling and testing. It treats noise not as something to block, but as something to neutralize through precise opposition. Instead of building thicker walls or louder audio, it subtracts unwanted noise from reality itself. Few technologies so directly reshape our sensory experience using such a simple but counterintuitive principle. Number 3. The Ion Propulsion Engine. The ion propulsion engine is one unusual modern device because it produces thrust without explosions, combustion, or even rapid fuel burning. Instead, it relies on forceful bursts of energy. It generates extremely small amounts of thrust continuously over long periods, allowing spacecraft to achieve enormous speeds over time. An ion engine works by ionizing a propellant, usually xenon gas. Xenon atoms are stripped of electrons, creating positively charged ions. These ions are then accelerated through an electric field created by a charged grid. As the ions exit the engine at extremely high velocity, they generate thrust according to Newton's third law. A separate electron emitter neutralizes the ion beam to prevent the spacecraft from becoming electrically charged. An ion engine will typically produce thrust measured in millinewtons, far less force than what would be needed to lift a sheet of paper on Earth. However, because the engine can operate continuously for months or even years, the total change in velocity it provides will far exceed that of a conventional chemical rocket once the spacecraft is already in space. Ion propulsion is not used to launch spacecraft. The thrust is way too small to overcome gravity. Instead, the engines are used once a spacecraft is already in orbit or on interplanetary trajectories. One of the most notable uses of this ion propulsion was NASA's Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres. Dawn used its ion engine to enter orbit around two different celestial bodies, something that would have been extremely difficult using conventional propulsion. The unusual nature of this ion propulsion does also extend to how it sounds or doesn't sound. Unlike chemical rockets, ion engines are nearly silent. There's no roar or flame or explosion. Instead, the engine emits a faint blue glow caused by excited xenon ions. This kind of visual appearance reinforces how different this technology is from traditional ideas of propulsion. Ion engines, though, do require significant electrical power to operate, typically supplied by solar panels or, in the future missions, a nuclear-powered system, and this power requirement does shape the spacecraft design and often results in large solar arrays that dwarf the engine itself. And because thrust is continuous and adjustable, ion engines allow extremely fine maneuvering. Spacecraft can make gradual trajectory corrections with high accuracy, which is valuable for long-duration missions. This engine is unusual because it redefines how movement through space is achieved. It trades power for patience, replacing explosive force with sustained precision. Instead of pushing hard for a short time, it pushes gently for a very long time, achieving results that would otherwise be impossible. Number 2. The Quantum Random Number Generator. The Quantum Random Number Generator. This is a very unusual device because it produces randomness that cannot be predicted, reproduced, or reverse engineered, even in principle. Unlike traditional random number generators which rely on algorithms or physical noise, quantum RNGs use fundamental quantum processes that are inherently unpredictable. Conventional computer systems generate random numbers using mathematical formulas known as pseudo-random algorithms. These numbers appear random, but they're fully deterministic if the initial conditions are known. In contrast, a QRNG draws randomness from quantum events like the behavior of individual photons or the decay of quantum states. A typical QRNG works by sending single photons towards a beam splitter. According to quantum mechanics, each photon has a truly random probability of being transmitted or reflected. Detectors record the outcome, assigning binary values like a 1 or a 0 based on which detector registers the photon. Because quantum outcomes cannot be predicted ahead of time, the resulting numbers are genuinely random. Even with complete knowledge of this system, no observer can predict the outcome of a quantum measurement. This distinguishes QRNGs from all classical random sources. Some QRNGs are implemented as standalone hardware devices, while others are integrated into larger systems. Commercial chips now exist and are used in data centers, research labs, and security infrastructure. Their outputs are often continuously tested to ensure statistical quality and absence of bias. Another aspect that's pretty unusual, a single QRNG device can generate millions or even billions of random bits per second, which far exceeds human-scale notions of randomness. These bits are used instantly by machines for encryption, authentication, and even simulation. But QRNGs raise some philosophical implications. Although the device itself remains practical, the numbers it generates are not just unknown, they're unknowable until they're measured. This makes QRNG one of the few technologies that directly operationalize quantum uncertainty into an everyday digital system. But despite their sophistication, QRNGs don't understand randomness, they simply convert unpredictable quantum events into usable digital output. This unusual nature lies in how deeply abstract physics becomes a practical engineering tool. In a world increasingly dependent on predictability and control, QRNGs stand out as devices that deliberately harness unpredictability, and they do so reliably. Number 1. The Tokamak Fusion Reactor. The Tokamak Fusion Reactor. This is one of the most unusual devices ever built. It's designed to reproduce the physical process that powers stars using controlled conditions on Earth. Unlike conventional power-generating devices, a tokamak doesn't burn fuel through chemical reactions or split atoms through fission. Instead, it attempts to fuse atomic nuclei together, releasing enormous energy in the process. The most advanced tokamak currently under construction is the ITER. It's located in southern France and it's operated by an international consortium. It's not just a power plant and will not produce electricity for the grid. Its purpose is to demonstrate that controlled nuclear fusion can be sustained at scale and generate more energy than is required to maintain the reaction. At the core of a tokamak is a donut-shaped vacuum chamber called a torus. Inside this chamber, hydrogen isotopes, typically deuterium and tritium, are heated to temperatures exceeding 100 million degrees Celsius. At these temperatures, matter enters a plasma state where the electrons are stripped from the nuclei and they move freely. Now, what makes this device unusual is that no material container can physically hold this plasma at those temperatures. Any solid wall would instantly vaporize. Instead, the tokamak uses powerful magnetic fields to confine and shape the plasma without letting it touch the chamber walls. Superconducting magnets generate these fields, which creates a magnetic cage of sorts that suspends the plasma in midair. The magnetic system used is one of the most complex ever engineered. They use a combination of toroidal and poloidal magnetic fields to stabilize the plasma and keep it circulating in a controlled loop. Even very slight instabilities can cause the plasma to escape confinement, terminating the reaction. Managing these instabilities is one of the primary challenges. ITER's magnets are among the strongest superconducting magnets ever built. They have to operate at cryogenic temperatures just a few degrees above absolute zero while sitting mere meters away from plasma hotter than the core of the sun. This extreme juxtaposition of temperatures, near absolute zero and over 100 million degrees, exists simultaneously within the same device. Fuel injection and heating is also highly unusual here. The plasma is heated using multiple methods, including powerful microwave beams, neutral particle injection, and even induced electrical currents. Unlike a conventional reactor, there's no chain reaction that has to be sustained through a physical containment. The fusion reaction stops almost immediately if the conditions are disrupted. One defining feature of a tokamak is that it's inherently safe in terms of runaway reactions. If confinement fails, the plasma cools and disperses in a fraction of a second. There's no possibility of a meltdown similar to fission reactions, and because the reaction requires continuous precise conditions to exist at all. ITER will use only small amounts of fuel at any given time, measured in the grams, yet during operation it's designed to produce hundreds of megawatts of fusion power output for sustained periods. This kind of ratio of output to fuel mass is one of the reasons fusion is pursued as a potential energy source. The Tokamak device is challenging conventional engineering timelines. ITER has taken decades to design and build, involving thousands of scientists and engineers. This complexity arises from not moving parts, but from the need to precisely control electromagnetic fields, plasma behavior, and cryogenic systems. Tokamaks are unusual because they don't convert energy in the way most machines do. They create conditions under which energy is released naturally from atomic interactions. And unlike reactors that operate continuously, tokamaks function in pulses. Each experimental run lasts seconds to minutes, during which huge amounts of data are collected. Every pulse is a controlled experiment probing plasma behavior, magnetic stability, and energy balance. As a device, the tokamak doesn't resemble a machine with gears, pistons, or visible motion. Its most important process is invisible. Magnetic fields shaping plasma, quantum interactions releasing energy, and control systems reacting in microseconds. The tokamak is unusual not because it's futuristic or speculative, but because it forces engineers to build a device around conditions that normally exist inside stars. Few devices exist anywhere where failure simply means the reaction disappears, leaving nothing behind. Fewer still require such precise balance that success can only be measured in sustained stability rather than output alone. The Tokamak fusion reactor is unusual because it's a device built not to dominate nature, but to cooperate with it. It holds matter in a delicate equilibrium where energy is released naturally, briefly, and under our control, hopefully.